In the previous section, we talked about variant types and learned how to use them to safely process our data. In this section, we will learn what polymorphism is and talk about a predefined polymorphic variant type option, which will help us to handle non-existent values in Reason. Let's start with this polymorphism. We've talked about Reason's strong type system several times already. However, types might force us to do unnecessary duplication. Let's say we have a function that swaps the position of values in a pair. We defined 3 versions of this function. Just to recap types syntax, we have a function which expects arguments x and y, which are, in the first case, integers. This second type signature defines what will be returned by the function. In this case, our function returns a tuple with 2 integers. All these 3 functions do the same thing. They swap 2 values. Each version of this function covers different types of arguments: integers, floats, and strings. As you can see, we are duplicating the same code 3 times just because of the types. Moreover, what if the 2 pair elements have different types? This would mean even more code. We defined another 2 versions of the same function just to handle the possibility that we are mixing integers with floats. Fortunately, we don't need to do this in Reason. And why? Because we have polymorphism. Let's take a look. Instead of explicitly writing types for x and y parameters as we did before, we write type variables instead. Type variables are written with a single quote at the beginning, as you can see here. And if they are letters, like in our example, A with quote and B with a quote, we read them as alpha and beta. The type syntax is saying that our function expects 2 arguments of alpha and beta and returns them swapped, first beta and then alpha. As a result, we can pass any types as x or y. This means we don't need all the previous definitions of the swap function, since we can pass integers, floats, or strings, or their combination to our swap function. Let's do that. As you can see, we can use our function to swap integers, floats, strings, or any other data type or their combination. This ability to use swap with many different types is known as polymorphism. So our swap function is polymorphic, and the nature of our swap function is defined by the types we pass as its arguments. When the compiler checks the definition of the swap function, all it knows is that x is some of arbitrary type alpha. so the compiler doesn't allow any operation to be performed on X that couldn't be performed on an arbitrary type. This means that the code is guaranteed to work for any X and any Y. However, we need to keep in mind that we must substitute type variables consistently. This means that our swap function cannot have this type, for example. This is not possible because this type of the function consistently substitutes only for the type variable beta and not alpha. When defining type variables, we are not limited to letters with quotes, such as alpha or beta. In fact, a type variable may be any identifier preceded by a single quote. Let's take a look. Instead of alpha and beta, we used identifiers first and second, and everything works the same. The compiler needs to have these identifiers preceded by a single quote, so that it knows it is seeing a type variable. As you can see, polymorphism is a crucial part of the language, and it will save us a lot of unnecessary typing. However, to really take advantage of polymorphism, we need to be able to define data structures whose types depend on type variables. Such types are called parameterized types, and Reason enables us to create them. Let's create one. We created the row type, which is a tuple of 5 components. It looks like we are passing a parameter alpha to our type. That's why this is called a parameterized type. You can think of this type as of a function expecting an argument and returning a new specific type. These arguments must be type variables, which are written using a single quote. So the row type works like a function expecting a type. Let's pass the expected type. We declared 2 new types using the row type. The first one is int row, which is a tuple of integers. We can say this type was returned when we passed an integer type as a type variable to the row parameterized type. The second type is string row, which is a tuple of strings. It was returned when we passed a string type as a type variable to the row type. Using parameterized types will save us a lot of typing, since we don't need to create separate types for int row and string row. We just reuse our row type with the different type parameters. Let's use our 2 types. We defined the identifier add numbers containing a value of type int row, which is a tuple of integers. We also created the identifier names containing a value of type string row, which is a tuple of strings. We can also write this more concisely. As you can see, we can pass the type variable to the raw parameterized type when creating an identifier. Normally, types are inferred for us by the compiler, so we can write this code even more concisely. As you can see, we haven't defined any types manually here, because the compiler inferred the type of odd numbers and of names identifiers for us. It's saying that odd numbers is a tuple of integers and names a tuple of strings. So parameterized types are one of the core features of the language itself. Without them, we would need to manually define several versions of the same type just to be able to use them with different types. This would mean a lot of duplicate code. In our example, we would need to define a unique type for every tuple containing different types, such as tuple of strings, tuple of integers, tuple of floats, and so on. With parameterized types, we don't need to do any of it, as you can see here. We should take advantage of parameterized types in our programs as well to write reusable code, which will help us to avoid unnecessary boilerplate. Reason also provides us with predefined parameterized variant types. We will talk about two of them, the option and list variant types. Let's get started with the option variant type. In other languages, we have ways to represent a non-existent value. In JavaScript, for example, we have null or undefined. This means when we have a variable of type string in JavaScript, this variable can be a string or null or undefined. We call such types nullable because their variable value might exist or not. The problem arises when we forget to cover in our code a case when the variable value is non-existent. This kind of situation is a common source of many errors, since we need to always keep in mind that all our variable values might be non-existent. Fortunately, Reason doesn't have nullable types. Every type in Reason is non-nullable. A string in Reason will always be a string and not a string or null or undefined. And this is a good thing, since this will help us to avoid many errors related to the existence of nullable types. However, even in Reason, we still need to be able to handle potentially non-existent values. And we can handle them using the predefined option variant type. Let's take a look. This is how the option type is defined in Reason. It's a variant with two constructors, none and some. So the value of an option type is either none or it's a value that is wrapped using some, as you can see here. This means whenever we are pattern matching the option type, we always need to cover these two cases. As you can see, the argument of the option variant uses a type variable alpha. So the option type is parameterized type with only one type parameter, which can have a value of any type. And because it's a parameterized type, we have only one option type in Reason, which can be used with different types. Let's take a look at an example. We have the identifier title. The compiler inferred that it has a type of a string. In Reason, this means this value cannot be non-existent. However, let's say we know that this value might be missing in some cases. We need to use an option type to address this possibility. Since we know that the value of title might be missing, we are using the option type. We have a condition is missing, which happens to be false. The value of this condition determines the value of the title identifier, which is an option. Here we have two scenarios that might happen. If is missing is true, this means the value is non-existent. We will use none to express that the value is missing. If is missing is false, this means the value exists. We will wrap our string with the option type using some. And because in our example the value of is missing is false, the value of title will be a string wrapped using some, as you can see here. And as you can see, the compiler is telling us that the title identifier is type of option with the type variable string passed to it. So we have the code which will determine the value of the title identifier. However, we will probably need to use the string value in our code later. And since the option type is a variant type with two constructors, as you can see here, we can use pattern matching to handle its value. We created pattern matching logic using a switch, and we covered both possible cases of the option type. When we have the value of title, meaning it's wrapped using some, we can extract it using a pattern. In our example, we will return a string describing this title. When the value is missing, we will return a different string describing we don't have the value. Because we used an option type for the title identifier, we forced ourselves to handle the none case. And by doing this, we removed any possibility of forgetting to handle a non-existent value. This means we remove the whole category of errors related to the non-existent values. Because if we forget to cover the none case, the compiler would tell us. Let's remove the none case from our example. As you can see, the compiler's exhaustivity check is telling us we forget to cover the none case.